Welcome to this video called Demystifying the Alpha Network Compiler, in which I'll try to explain some of the details of the Drools rule engine. Let me start with a quick introduction to Rete nodes. Drools is a rule engine based on Freak, an evolution of the original 1974 Rete algorithm by Charles L. Forgy. In this video, we're going to take a deep insight to some of the internals of the system and to a specific feature called Alpha Network Compiler, which has been present for quite a while in the codebase, but only recently has started to be used actively. Rules evaluation in Drools is based on a data structure called Rete, that means network in Latin, which is a discrimination tree comprised of different possible kind of nodes. Here are some examples of such nodes. There are object type nodes, alpha nodes, rule terminal nodes, beta nodes, and other kinds of nodes. The Alpha Network Compiler is an optimization that is effective when the Rete is assimilable to a pure alpha network only, which is a shortcut to say it's a Rete consisting only of object type nodes, alpha nodes, and rule terminal nodes. In this article, for the sake of simplicity, there won't be any references to other kind of nodes. When dealing with Drools rules evaluation, it's useful to see the relationship between the nodes in a graphical way, so here's an example of a very simple Rete. You can see the various kinds of nodes are colored in different ways. Object type nodes, also known as OTN, are pink, alpha nodes are blue, and rule terminal nodes are green. We have a yellow node called entry point, which is where the evaluation of a rule starts. Every object, sometimes called fact in Drools, inserted inside Drools working memory is evaluated against each node in order. If the evaluation succeeds, it's propagated to the next one until it reaches the rule terminal node. In the article linked, you will find also the references to the original source code of Drools, so that you can check how the real production code works. What is an object type node? Think of an object type node, sometimes called OTN, as a Java instance of operation. If an object matches the type defining the OTN, it will enter the Rete from that node. There's one OTN for each Java type defining each pattern. If two rules have two different patterns on the same object type, then only one OTN will be created. What is an alpha node? Alpha nodes represent a constraint inside the network. Example of a constraint might be age greater than 30, name equals Luca, or surname starts with M. When a Drools pattern has two different constraints, then one node for each constraint will be created. So this example, person that has two constraints, name equals Luca and surname starts with M, will generate two different alpha nodes. In the diagram shown before, we have a pattern with three constraints, therefore that we require a total of 3 alpha nodes. A rule terminal node represents the end of an evaluation. In this article, we'll deal only with alpha terminal nodes, which represent the ends of the evaluation of an alpha network. During a typical Drools evaluation, the terminal nodes interact with the agenda, which is the data type we use to synchronize the consequence of the rules. But here we skip the explanation of the agenda, as it's not useful to the purpose of this article. Let's see the first optimization of a Rete network, the alpha node sharing. As we said before, each constraint inside a pattern will generate a single alpha node. But when constraints are identical, even among different patterns and rules, only a single alpha node will be created. In this example, only 3 alpha nodes will be created. As the first constraint person name equals Luca is identical in both rules, it generates only one alpha node, while the other two constraints, age minus the 30 and age greater equals than 30, will generate one alpha node each. Here's a diagram to represent such node sharing. But what does actually mean to evaluate a node? It means to propagate the call of a method recursively in the next node of a tree. If we want to code this in a simple way, we might think of a common interface for Drools nodes. This interface will have the method that we need to propagate among nodes to evaluate the Rete. In this case, it's called assert object. Each node will implement this method in a different fashion. Here's an example on how we could write a simple object type node. We create a class called Drools object type node that implements the Drools node interface, that means that implement the assert object method. In the constructor of the class, we pass a class reference and then the next node to be evaluated. And here's an example on how we could implement a simple alpha node. We create a class that in the constructor takes a Java predicate and the next node to be evaluated. And in the assetObject method, we test our predicate against the input object. If the test is succeeded, the method is propagated against the next node. After being evaluated in an object type node, the OTN will call assetObject on the first child, which will evaluate the constraint, in this case a simple Java predicate, to eventually propagate the assertion to the next node. When the last node is an alpha rule terminal node, the evaluation will end. Here's a stub implementation of a terminal node that doesn't do anything at all. When there are multiple non-related alpha nodes, each alpha node will be checked against the input object. This is not efficient as we need to check a predicate that could be expressed in a Java with a simple if, using dynamic dispatch against every single alpha node. This is due to the fact that the JVM doesn't know the concrete implementation of a Drools node interface. The code shown in this video is simple enough and works well for demonstration purposes, but is terribly inefficient. Consider that a common Drools project might have thousands of alpha nodes, if not more. Here's an example of a brute force evaluation of all the constraints. We changed the object type node to add a list of alpha nodes as a second parameter of the constructor. After having checked what type the object actually is, we call assetObject on every other node. Hashing is one of the first optimization that is implemented in the current code base. When a field is hashable, for example when dealing with strings and integers, after a certain amount of alpha nodes, the system will keep an internal map of nodes using the fact value as the key. This improves the evaluation of a fact against multiple alpha nodes. A simple get in the map will bring us the correct next node to propagate the object to. When we build the Rete, we could do something similar to this snippet of code, assuming that we have buttons that check strings that are equals to 10, 12, and 30. After having built the Rete in this way, the evaluation will be much faster using the mapGet method. What I wanted to show you is just one of the optimization that is in the code base. There are many more, and most of them are specialized in collapsing the search space, effectively reducing the number of the evaluations. The Alpha Network compiler leverages the Java code generation to have a faster evaluation of the constraints. It supports most of the optimizations that are usually applied in memory, such as the hashing explained before or the range indexing, creating a snapshot of the code that is heavily optimized. Here's the Java code produced in the worst case scenario. Given this rule, when there is a string that has the length greater than 4 and smaller than 10, and we assume that these constraints are indexable, it will generate this code, which is basically a Java nested if using constraints instead of if conditions. As you can see here, there are no alpha nodes in this propagate assetObject compared to the non-materialized version. The constraints are unwrapped from the alpha node and set as a field of a class. The order of the ifs will be determined by the alpha node sharing optimization we saw before, so it's faster than evaluating the ifs in a brute force order. For example, these rules with one identical constraint will generate this Java code. As you can see, there is an external if that maps to the age greater than 20 conditions and then the two specific ifs afterwards. Let's take a look at the inlining. A more interesting fact happens when we have multiple hashable constraints, as we saw before. Let's take as an example these rules. These rules have each a different pattern on the same field called name, but we have 3 different strings. This will generate this Java method instead. By inlining the strings as keywords inside a switch statement, we leverage the Java internal dispatch to get even faster results. We have provided a benchmark that demonstrates that this approach is faster than the worst case brute force. Here's the results. So how to use the Alpha Network compiler? To try the Alpha Network compiler in Drools, you can check the ANC documentation link in the article and the test in the Drools Alpha Network compiler in the repository. Let me show you how we use the Alpha Network compiler. There is an ongoing work for an experimental feature in the current Drools codebase in which we will use the Alpha Network compiler to evaluate a DMN decision table in the fastest way possible. Here's an example of such table. If you need more information on what a DMN decision table is, check the DMN documentation in the article. We parse a DMN decision table, and for each cell we generate an alpha node with a constraint. Then, after a round of node sharing, we give the alpha node as input of the ANC and we generate the class using the output of a decision table as a rule terminal node. We created a benchmark out of our pragmatic use case and confirmed that this approach is indeed faster than evaluating a decision table with a brute force approach. The current implementation is still a proof of concept and not production ready, but certainly the performance metrics collected demonstrate the benefits. Then we'll further evolve it to have the fastest decision table evaluation we can get, leveraging all the optimization we showed in Drools before. Here's an example of what we produce. We have the field constraint greater equals than 18 translated into Java code. Then we have one of the classes that we generate to create the Rete network. As you can see, for each row in the decision table, we create a series of alpha nodes using the create alpha node method that supports the alpha node sharing, and then we link the nodes together, creating an alpha network. At the end, we add a rule terminal node with the result, in this case, approved. We have a class that assembles the evaluation. This generates the Rete in the initerated method and evaluates it in the evaluate method. And finally, here's part of the compiled alpha network. Only a few of the constraints in the fields are shown. The interesting part is in the propagate offset object method. Even though this specific example doesn't support inlining, we can see it's exploiting the alpha node sharing to reduce the number of the evaluation compared to the original brute force evaluator. Let's talk about further improvements. We don't consider compiled alpha network only as a performance optimization, but we think in the future it could become also a lean representation of an alpha network without using the full Rete. The work of the DMN alpha network is still a work in progress. We still need to support all the possible hit policies and moreover move most of the generation at compile time, so that when instantiating the compiled alpha network you don't need the full Rete. Currently, this is not doable. If you check the set network node reference that unwraps the constraint in fields, you can see it takes the node of a Rete as an input, but this is totally avoidable. We could also inline the constraints and therefore remove in lambda constraints that use the virtual table indirection we discussed before. Let's get to the conclusion. We saw some of the internals of Drools describing a simple way to evaluate a Rete network, some of the optimization we use in memory, and some of the optimization used while generating the compiled alpha network. After that, we saw an experimental usage of the alpha network to evaluate in an efficient way DMN decision tables.